Hi, my name is Carlos, and I'll present our work on spectral image tokenizers. This was done with my collaborators Suhail and Amish. The context of this work is two-stage autoregressive image generation, where we first train a tokenizer to map images to a sequence of discrete tokens, and then train an autoregressive transformer to generate those tokens. We introduce a multi-scale tokenizer that handles images of varying resolutions, with the property that the prefix tokens are the same across resolutions. So increasing the input resolution corresponds to appending tokens to the sequence. Our multiscale detokenizer has a similar property. Taking a prefix sequence reconstructs a lower resolution image, and longer prefixes reconstruct higher resolutions. These model properties are by design, not learned. We train a generative autoregressive transformer on these sequences. It inherits the multiscale properties of the tokenizer. Here we can decode a partially generated sequence to obtain a lower resolution image. And we progressively decode higher resolutions by generating more tokens. One downside of typical autoregressive image generation is that the next token prediction is conditioned on a partially generated image. Diffusion models condition on noisy full images which capture low frequencies. Our model combines diffusion-like conditioning with an autoregressive transformer architecture. One practical application of our multiscale generation is fast preview. We can quickly generate multiple low-resolution images for some prompts and pick our favorite to continue the high-resolution generation. Another application is upsampling. We can tokenize a low-resolution image and use ARSIT to generate the corresponding high-resolution image. Image editing is another application. We tokenize a given image, discard the high-resolution tokens, and generate replacements with a new prompt. Now let's talk about how our model works. In a typical VAT-VQ GAN, the transformer input sequence is made of image patches. Our main modification is to take patches from the image's discrete wavelet transform instead. We make the patches larger for higher frequencies since they can be compressed more aggressively in natural images. Now, we want to ensure that the low-resolution tokens are the same for low and high-resolution versions of the same image. To enforce this property, we introduce a scale-causal self-attention mechanism where high-resolution tokens depend on low-resolution tokens, but not the other way around. Here we show comparisons against a fair baseline. Our tokenizer reconstruction is significantly better and faster at low resolutions and matches the baseline at higher. The solid lines are ours. For generation, our metrics match the baseline while being significantly faster at low resolutions. We evaluate on the same settings of prior state-of-the-art autoregressive image generation, VAT-VQ GAN, Party, and LlamaGen. Our method is competitive while having additional multi-scale capabilities. Here are some examples of multi-scale generation where the number of generated tokens increase from left to right. Here is upsampling from 32 by 32 inputs with the ground truth on the right. This is upsampling from 16 by 16 inputs. And some editing examples. The input is on the left, the output is on the right. A limitation is that the scale causal attention enables the multi-scale properties, but it slightly harms reconstruction. And we only use small generative models here, so it's unknown how this method scales. And the question whether diffusion or autoregressive models are best for image generation is still open. Thanks for watching.